Hello, we're doing checkpoint 5.18. They want us to evaluate this double integral over a region R, 4 minus x squared minus y squared dA, where R is a circle of radius 2 on the xy plane. So whenever we're dealing with circles and things that might look like polar coordinate or can be easily described in polar coordinates, and I think it would be a great idea to go into polar coordinates. And we want to establish our information about your radial or your region, and for that we can describe that easily with constants. 0 to 2 for the radius, and theta goes all the way around from 0 to 2 pi. Now, one thing to note about these things is that when you're dealing with, if this was in Cartesian coordinates in x and y, you'll have the complicated x squared plus y squared is equal to 4 function to deal with. And so that, in trying to describe that, could be kind of tricky. Okay. Now, in doing so, we also, in changing into polar coordinates, we also need to deal with the x's and y's that are kind of sitting here as x's and y's. And so we kind of remind ourselves that r squared is equal to x squared plus y squared. And so we have both x squareds and y squareds are negative, so this is essentially negative r squared. And then we can set this up. Okay, so setting this up as our double integral, we're going to change this into 4 minus r squared, as we stated. And now our dA is going to produce an extra r before we get to the dr d theta. Now our limits go from 0 to 2, and our theta limits go from 0 to 2 pi. Okay. All right. So that's your double integral now fully in polar coordinates. And I would like to point out another piece of information, or another neat little trick, in that if you have factors here, like this thing does not have any thetas at all, so you can imagine this integral with the dr is constant with respect to theta. We can actually move that out, and then you can have the integral of d theta by itself. So integral from 0 to 2 pi of d theta by itself that you can multiply, and then you have the rest of this integral from 0 to 2, and I'm going to go ahead and distribute the r, so I have 4r minus r cubed dr. So dealing with these two integrals separately turns out to be easier than trying to do an iterated integral. Not that the iterated integral is that difficult, it's just going to be easier to kind of maneuver and look at. In fact, this is just going to be 2 pi, so this is going to be theta evaluated at 2 pi and then evaluated at 0. So this is just 2 pi, and then we're done with that. Here, we'll take a few more steps. When we integrate, it'll be r squared over 2, and then there's going to be 2 left, 2r squared, and then this is a 1/4 r to the 4th. We're evaluating from 0 to 2, and we know that 0 is going to disappear, so putting a 2 in here, we're going to get 2 times 2 squared is 4 times 2 is 8. And then 2 times 2 is 4, times 2 is 8, times 2 is 16. 16 over 4 is 4. And then that's it. And so this turns out to be, 4. And then we have 2 pi times 4. So then our result will be 2 pi for the first integral, 4 for the second integral, and then we have 8 pi. And then that's it. Okay. I hope that helps.